Recording in progress.
All right, so here is a problem, a register problem. I'd be very surprised if you don't have a register problem. Usually he has one on these tests. I just actually bumped into him walking, and I did not ask him what was on the test. Sorry, might have been useful. Okay, so the register below can hold its value or load a new value in parallel. So he's giving you an example of a register. Then he's saying draw a similar register that can hold its value or shift right with serial inputs SEER in and serial outputs SEER out. So this is just an example for you to use, and it doesn't have to be exactly like that, but this is what we're going to go with. So our job is to shift right with serial input in and serial output out. Oh, so it can either hold its value, or shift right. And when you shift right, you can either shift right and then like shift something out and something in, or you could like wrap around. And this one is saying you have an input and an output, and I'll show you what I mean by that. So it's saying to make one similar to this, so I would assume it'd be a 3-bit. So a 3-bit register means you're going to have 3 flip-flops, and I'll label them D2, D1, and D0. And whenever you have a register that can do more than one thing, each flip-flop will have associated with it a multiplexer. So if you have a register problem, you can always do what I'm doing right here to get set up while your brain is thinking about it, especially if, like me, you get test anxiety. This is something you can just, this is going to be how it gets set up. And you'll get some points for doing it. You'll have a clock. And you'll have your outputs. And the output from the multiplexer is the input into the flip-flop. And this is going to be pretty much your setup for most registers. Now, if you look at the example I think I did if you were at the session, the example I did of the session, there was one that we set it up. We were writing it from Verilog code, and we ended up not needing one of the multiplexers. And if you don't need it, you can erase it, but this is a good kind of setup. And then you'll have some variable that tells you which of these you use, whether you use the 0 or the 1. And that variable is in this circuit that I'm looking at right here. It's the one, he has it gone into the bottom of the multiplexer. I usually have them going into the top. And you might be given a variable name or you might not. I will just call mine signal. And this does not specifically say whether it should hold its value if the input is 0 or shift right if the input is 1. So you can just decide. If it does tell you, then you would use what it tells you. So let's just say holds its value if signal equals 0 or shift right if signal equals 1. Okay, so if signal equals 0, it holds its value. And so that means this 0 means that I want to have the input into the 0 port of the multiplexer the held value. And so the held value means it's going to be the same as it was before. And so the Q2 will go into the 0 port of its multiplexer, Q1 goes into the 0 port, and Q0 goes into the 0 port. So that means if signal is 0, then the input into each of these flip-flops is what its output was before, so it just holds its value. Now, to shift right means that D2 goes to D1, D1 goes to D0, and then we have an input to go to D2, and we'll take the output from D0. So, and that's if signal is 1. So that's going to go into the 1 input of the multiplexer. So what goes into the 1 input of this first one is the variable serial in, and coming out of this one is the variable serial out. And that's drawing the circuit. And the next thing that we're going to do is we're going to look at some Verilog for a register and draw the circuit that goes with that. So before I get that Verilog, are there questions on this? Looking for the chat, nothing there. Okay, well, let me get the question on the Verilog.
That one is done?
That one's done.
So it just gives you a register that tells you to build one that shifts the value.
Yeah, well, this one was to shift the value. He could have it do other things. The example that I did, I had it do all kinds of things. This one, the one up here, loads in parallel. And so you see how it has R2, R1, R0. So that's actually, that's a parallel load as opposed to a serial shift. Okay, so let's do this one. And so I know that this is going to be a setup like with a register because I see this vectored signal and I see the y's, y0, y1, y2, and that it's equaling some various different combinations of the others. And so this is not going to be a shift register, or it's not going to be a parallel register, because I'm not doing the same thing to each one of them. Like if it was, if I was to write the code for a shift register, I'd probably have a for loop, and I would say, I would have it go from, have J go to J plus 1, or from J plus 1 to J. This is doing something different for each flip-flop, and that's fine. So, but when I see a setup like this, I know that those are D flip-flops. So just like last time when I said you can just, how to kind of get started, I know that these are going to be D flip-flops. I don't think I've done this particular problem in years, so D2, D1, D0. So I'm not entirely sure how it's going to end up. But I know I want to have this set up. And for this one, I'm going to look at this line right here. It says positive edge of clock. If it had said negative edge of clock, I would put a little bubble on each one of these. That would make it on the negative edge of the clock, but it says positive edge of the clock. And now let's see. If load, okay, it's got an if. When I see that if, that tells me I do need multiplexers. At first, I didn't think I needed them because I didn't see the if or a case statement. But an if or a case statement usually means you need multiplexers.
If or what?
Case.
Basically.
And my if, I just have an if and an else, so that means a 2-to-1 multiplexer will do fine. If I had, you probably would not have one on a test that had you have all kinds of different possibilities, but I don't know why it does this. And it says if load. So if load means my variable name is load. So that is my select for my multiplexers. And so if load is 1, then Y, so it says Y becomes the binary number 100. So this is Y0, Y1, Y2. So I want to load 1 into Y2. So this will be 1, 0 into Y1, and 0 into Y0. And those are all at 1 because it said if load. That means if load equals 1. So that's a parallel load. We're just, if load is 1, it just loads those values. And the multiplexers, the output for the multiplexer is the input for the flip-flops. And then else. So now where if load equals 0, so now this is going to go to the 0 port of the multiplexer. Y0 becomes Y1 or Y2. So I will get here's Y2, here's Y1, and that becomes goes into the 0 of Y0. Y1 becomes Y2, so I'll just come out of Y2 and go into the 0 there. And Y2 becomes W, so I have another variable W, and that goes into the 0 port there. It does not look like in this particular circuit I'm doing anything with this output, but it's there. And that's everything that I would need for this particular
So
circuit.
you got the gate from on the code. Is that a bar?
Yes.
Oh, okay.
So or is that, and is the ampersand.
Yeah, I got you. And then not's like the exclamation or
Not is usually a tilde. It's different logical and or and not, like if you have an if statement, if this and that, I think is 2 ampersands. And
Yeah.
but if you're just anding or oring bits, you can use a single one. Okay, any questions on that? All right, I'm going to stop this and